All right, let's go on page 49 when we are done. And we're reviewing exponent rules because, well, they're important, but mainly because one in particular that we are going to be using with exponentials, I know you're familiar with, I know you understand it, but we're going to be doing it backwards. And if you don't understand how it connects to the one that goes forwards, then it just makes it a little bit more confusing for you. So we're just going to go ahead and review them all. So hopefully we won't make a bunch of mistakes. As we're going through this, if you're like, this is so easy, it's ridiculous, then that's good. You really kind of should have that feeling, but I don't know that everybody's going to feel that way. So, all right, so let's first talk about the product rule. So I have A is not 0, because if A was 0, the whole thing's 0, right? But I'm multiplying two terms with the same base, and so then our rule is to keep the base and add the exponents. A to the m plus n, right? Again, a rule you've known for quite a while. We use a lot. I don't think that you normally mess that one up, because if I have x to the 5th times x to the 7th, I don't think any of you at this point would still be trying to give me x to the 35th, right? We keep the base, we add the exponents, we get x to the 12th. Everybody agree with that? No brainer, right? Piece of cake. All right, so then what if I had, for the second one, x to the negative 6th times x to the 10th. Now, we have a rule for negative exponents, but I don't necessarily need to use that right now. All right, there's no reason to get fancy with anything. I can use my product rule again, which means I keep the base and I add the exponents. And what's negative 6 plus 10? 4. It's x to the 4th, and I didn't even have to know my rule for negative exponents. Okay, make sense? There's no reason to make it more complicated when it doesn't need to be. All right, so now this is why we're actually going over all of this today. If I have 3 to the x plus 3 power, okay, let's say that I have that. Instead of combining them, I want to separate them. So I want to take what I have that looks like this and make it into that. So this is what I mean by using the rule backwards. If I have two terms with the same base and I keep the base and add the exponents, then I should be able to take it back apart. I have a base that has an exponent that has addition in it, so I should be able to break that up into 3 to the x times 3 to the 3rd. You see how that works? And we're just going backwards. So I want to make sure you understand it's not a new rule. It's a rule you've already done 5 billion times. We're just going the other way, and you've probably never gone the other way before, and that's okay. Okay, because we're going to do this a lot with exponentials. You're going to use it in calculus with E, mostly with E, but maybe with some other things. And so just want to make sure that you understand we're not making, there's no magic happening anywhere, right? It's just our rules. But then we can clean this up a little bit more. What's 3 to the 3rd power? 9. No. 27. 27. So I can make that 27 times 3 to the x power. And then do you see how that looks like one of those little exponentials we were doing? This is like an exponential that has a vertical dilation. This is an exponential that has a horizontal translation. If I was to graph this and graph this, I would get the exact same thing. They look completely different, but we just use those rules and we can see that they're the exact same thing. Okay, we good on that so far? We'll talk more about that later, but do you understand how the rule works at least? Okay. All right, so then we have our power to a power rule. A to the m power to the n power. So power to a power, that's when you get to multiply. So you get a to the m times n power. So if I have x to the 5th to the 3rd power, right? Power to a power, you just multiply. That's all there is to it. This is x to the 15th. If I have p to the 3rd power, all to the 1/3 power, what's that going to give me? P. It's just like p to the 1st power, right? It's just p. What's another way to write something to the 1/3 power? Cube root, cube root. So if I had p cubed and I took the cube root of it, the cube root's how you undo a cube, right? And that would just give me p. And that totally makes sense to us, but that's what's happening here with these exponents as well. Okay, that's why it works like it does. Any questions? All right, good deal. Okay, so then product to a power rule. A times b to the m power, I can distribute that exponent and get a to the m times b to the m. I think you're pretty good at that one too. The problem is you get it mixed up and you try to apply it sometimes when it doesn't work, and it would be in something like this. If I had a plus b to the m power, that does not equal a to the m plus b to the m. That gets you sent to math jail, no parole, okay? Because that's bad. Bad, bad, real bad. Not if you have addition or subtraction, you cannot just distribute that exponent. Only works if there's just multiplication. Okay, we good on that? Because that's a huge mistake that happens all the time. Makes me want to scream. Okay, don't do that. That's bad. All right, so what if we have x squared times y to the third power? Can distribute that exponent, but then it's like in a power to a power situation. So this would give me x to the what? 6th. Good. Y cubed. This is a power to a power, so you multiply. You only add when you're multiplying two numbers with the same base. This, when I distribute those, it's basically this rule right here, because it's a power to a power. Does that make sense? Good question. All right. Second one, let's do 3 times x to the 4th to the third power. So I can rewrite that as 3 to the 3rd times x to the what? 12. Okay, good. And then what is 3 to the 3rd? 27. 27 x to the 12th. Everybody okay with that? All right, good deal. Then, what if I have 3 square root of 5 squared? Okay. So that's two things being multiplied inside. So I'm going to distribute that square. So that's going to give me 3 squared times the square root of 5 squared. What is 3 squared? 9. What is, that one's fine. What is the square root of 5 squared? 5. And 9 times 5 is 45. Any questions? It's the square root of 25, which is 5, but we can skip all that. Okay, 0 exponent. If a does not equal 0, then anything to the 0 power is what? 1. So if I have 5x to the 0 power, I can use my product power to a product rule, and that gives me 5 to the 0 times x to the 0. So what's 5? Those look like 6s. Handwriting's bad. 0, x to the 0. All right, what's 5 to the 0? 1 times x to the 0, which gives me 1. Okay, and you could have skipped all that inside stuff too, but that's the way it works. All right, but if I have 5 times x to the 0, is that going to give me the same thing? No, because parentheses matter, right? This is going to be 5 times 1, which is just 5. Okay. Any questions at all? We're good? All right. Flip it over. Let's look at the quotient rule. Okay, so the product rule was we had two terms that were being multiplied, kept the base, and we added the exponents. This is two terms being divided, so we keep the base and we subtract the exponents. M minus n. So if I have x to the 12th over x to the 5th. The x to the what power? 7, because you just subtract the exponents. All right. If I have x to the 5th over x to the -1, so there I am again with the negative exponent. Do not need to know my negative exponent rule right now. I can just subtract the exponents, and 5 minus a -1 is x to the 6th. Good. All right. Now, even though we know that this is the rule, sometimes there's people that don't really understand why. And maybe it's because nobody's really ever shown you why. They just tell you these are the rules. So we're going to do another easy one, then I'm going to show you why the subtraction actually works. So we are going to go ahead and write out 5x's in the numerator, because x to the 5th is just x times x times x times x times x, right? 5x's. In the denominator, I'd have 2 of them. Then we know how to cancel things, right? I can cancel this x with this one and this x with this one, right? Because I can cancel each one of them out. That leaves me with 3 in the numerator, which is x cubed. I do not suggest that you write it out like that every time, but that's what's happening. It's like you're taking that many and you're subtracting them because you're canceling them out. Okay? We good? Okay, perfect. All right, quotient to a power rule. It's pretty much just like your product to a power rule. I get to distribute that exponent, and I get a to the m over b to the m. So if I have x squared over y to the 3rd power, still going to have a fraction. Numerator would become x to what? 6, because it's power to a power, right? And then the denominator would be y cubed. Okay, if we have x over 2 to the 5th power, so in the numerator, I will get x to the 5th. In the denominator, I get 2 to the 5th, which is, what is 2 to the 5th?
32.
32, very good. Okay, then last one of these. If I have 4 over 9 to the 1/2 power, that's going to give me 4 to the 1/2 power over 9 to the 1/2 power. What is 4 to the 1/2 power? 2. 9 to the 1/2 power? 3. It's the same as taking the square root, right? You done? Yep. All right. All right, negative exponent. So a is not 0 again. M is a positive real number. So really what the negative exponent does is it gives you the reciprocal of whatever the base is. That's one way to look at it. But it does just move from the numerator to denominator and vice versa. When you move the location, the sign on the exponent changes. The sign on the exponent does not affect the sign on the number. So a to the negative m power is the same as 1 over a to the m power. And 1 over a to the negative m power is a to the m power. And we're going to do more than 3 little examples here because there's a lot of stuff that goes on. So let's start with a couple really easy ones. If I have x to the negative 3 power, I really just want the reciprocal of x, so that's 1 over x cubed. So the exponent stays on the x, but when it goes from the numerator to the denominator, the negative is gone. Okay, we're good on that? Should look familiar, I hope. Okay, what about 1 over x to the negative 4th? Okay, that 4 is going to stay on the x, but the whole term is in the denominator, so it comes out of the denominator, goes to the numerator, and I get x to the 4th. Okay. All right. Then, if I have 1/2 to the -2 power, so that negative, I'm going to deal with that first. That gives me the reciprocal. So the reciprocal of 1/2 is 2, so that'll give me 2 squared. And then that gives me 4. All right, those of you that have quizzes, your time is up. All right, any questions on that one? All right, 4. 3 to the -2 power. Okay, I'm going to deal with the negative part of that first. That becomes 1/3 squared, which then gives me 1/9. So especially with the negatives, do it a step at a time, even if you think it's easy in your head, because that's where, again, ridiculous mistakes happen and you start changing signs on the values and things like that. All right, 5. If I have x to the -2 over y squared z to the -3. Okay. If you start with a fraction, again, there's no addition and subtraction. It's all just multiplied. Just go ahead and start with a fraction bar here. That x to the -2, he's in the numerator. He needs to go to the denominator, which makes the exponent positive now. Y squared has a positive exponent. He stays down here where he is. The z has a negative exponent, so he moves to the numerator, and the exponent becomes positive. Okay, that makes sense? All right, and then one last one here. If I have x to the -2 over y squared. I'm going to do the same thing, make my little fraction bar. X to the -2 power means he comes to the denominator, becomes a +2. Y squared stays down here. Then what? 1 in the numerator. Okay, so the reason I did this one, which I know is a lot like number 5, is that sometimes, especially if you didn't start off with a fraction bar there, some people would just give me the answer like x squared y squared is the answer, and it's not. It's 1 over that, or sometimes people put 0 in the numerator, and that's not okay either. Okay? So, it's not okay. All right, we good? Any questions? Okay, perfect.